Hi, this is the first video on queuing theory or waiting on lines, and basically what we're going to do in this is talk about some areas of application, terminology and notation of queues, talk about some basic properties, general properties including Little's formula, and we'll talk about 5 basic models, focus on these 5 models, and then talk about some economic analysis for queues. So that's the plan for this series of videos. Start with defining what a queue is. So queuing theory is the study and analysis of waiting lines, and of course everybody has waited on lines, and I'm going to use as a model that referred to as the bank teller, where we can have one teller or more. The objective here is to design a queuing system to help an organization perform optimally according to some criterion regarding wait time, service level, line length, profit, probability of how long a customer has to wait. So often we have conflicting goals, because if we want to reduce waiting times, which means improve service, that means we have to hire more people, more servers, and that costs us more, higher operating cost. So we want to balance that trade-off between good customer service or lower waiting times and operating cost, the cost of providing the service. So queues apply in many areas, so I'll just go over some quickly here. There are some commercial applications like a barber shop, bank teller, checkout stands, cafeterias, so on. In transportation area, queues, you'll find queues in toll booth, landing, loading facilities, airports, parking lots, and so on. In business and industrial service systems, material handling systems, maintenance systems, computing facilities, internet was a prime example where there's a lot of queues back and forth. Social systems, where you have judicial system, the legislator, where the bills wait to be acted upon by the legislator. Healthcare systems, and low and moderate income housing facilities, and so on. Communication systems, telephone networks, internet services, satellite communication systems, and so on. So the applications of queuing theory are endless. Now, what are the basic terminology and notation for a queue? Here is a sketch for a queue, where first thing, our customers arrive at a facility where they receive service and leave. And the first thing is the input source, where customers arrive from. So this is the source where potential customers that go into the system. Think of a bank teller. These are the customers that go to have transactions. They arrive here at the service, and the service facility or the queuing system itself is made up of the queue where customers physically wait, and the service mechanism. In our example are the tellers that provide the service, and then customers leave after they complete the service. So to identify a queuing system, we need to identify the input source or the population. We need to identify the queue and the service mechanism. Okay. So the input source, I'm going to talk about each one of them briefly. That customer. This is the arriving unit requiring service. It can be. It doesn't have to be always a human being. It can be a machine that requires service, or a phone call being routed through the network. That can be the customer. The population of potential customers can be finite or infinite. So if we have a lot of customers that can go require the service, we model it as infinite, although it's physically it's not necessarily infinite. Arrival pattern, customers arrive, can be one singly or in bulk, like buses arriving at a bus station. We talk about inter-arrival times. Times between customer arrivals can be deterministic, or it can be stochastic, which means a source of randomness described by a probability distribution. The service mechanism, talk about the service mechanism here, which consists of one or more service facilities, each of which contains one or more parallel service channels called servers. So server, if I have a bank teller, I can have a single teller, that would be a server. If I have two, they are called in parallel. Sometimes you have servers called in tandem, like in machine handling systems, where a part going through a series goes to the first machine to have something done and goes to the second machine. So the machines are servers, but they function in tandem or in stages. Now, how do we select waiting customers for service? There are several disciplines. First one is called the most popular. It's called first come, first served, which applies to human beings because we don't want to violate that, because it violates the principle of social justice. But if customers are not humans, we have other options like last come, first served, which is what really happens inside a computer system with paging, where information filed at the top level being used first. With service in random order, where customers are selected in random order, or in round robin, cyclic service. This is what large computers or supercomputers use to provide service for different programs that want to run, which basically it gives one little quantum, one thousandth of a second to one job, and then gives the same amount of time to the second job, and so on, and then it keeps rotating among all of them. And of course there are priorities sometimes, so you want to give priorities to a certain class of customers, like patients arriving at the emergency room. We give priority to more urgent cases than patients who just need less. Patients who have a heart attack has higher priority than a patient who probably just needs having a headache or so on. So also priorities can be preemptive. So if a very urgent case comes in, it preempts the lower class level, or non-preemptive. You finish the job you're doing and then you give high priority to the more urgent customer next. Okay. Service time is basically the processing time or the transaction time, which is the time you need to receive the service. It can be deterministic, like if a machine is doing the job and it exactly takes the same amount of time to do the same job repeatedly, that we call that deterministic or stochastic, which is like what happens at a bank teller. Different customers need different amounts of time. So we model that as a probability distribution. And you noticed here, every time we have a source of randomness, a stochastic or source of uncertainty, we model it as a probability distribution. The queue, which is the waiting space, the physical space where customers wait for service, we call that, can be finite, which is f minus k. F is all the space available, including service times. So if you have 5 customers waiting and 2 servers, that makes f7, but we have 5 waiting spaces. Or it can be infinite. That's if really the waiting space is large enough, it never fills up. So we model it as infinite because it's easier that way. So we can have a single queue feeding all servers as we see in a bank teller, or we can have multiple queues like we see at McDonald's or at grocery stores. discipline, which is behavior of customers with respect to servers. Sometimes customers bulk, refuse to enter the system if it's too busy. Line hopping, call it jockeying. Aborting, they wait for a while and they decide to leave the service. Now we can talk about operating characteristics. These are non-financial, just steady state descriptors of system performance, and these are very important to really memorize and keep ready so you can use them anytime we need to. So rho, which is a Greek letter rho, it's the percent utilization of the service facility. So rho can be like if the bank teller is busy 90% of the time or 80% of the time, we call that the utilization, okay, of the server. Percent, or the probability the server is busy. L is the mean number of customers in the system. So that's on average how many customers are in the system, including the queue, those waiting in the queue plus those in service. LQ is the mean number of customers in the queue, so those are just waiting, they are not in service. W is the mean waiting time in the system, how long customers on average wait in the system, in queue plus in service, so that includes their service time. WQ is just the time in the queue, the mean time in the queue, excluding the service time. And Pn is the probability that there are exactly n customers in the system. So if I calculate P0, P1, P2, P3, that I get the probability distribution of the number of customers in the system. Pw is the probability that an arriving customer has to wait. So that's the probability of a customer arrives and finds nobody in the finds the server busy, right? Okay, so we need to compute all of these performance measures for specific queuing models, but to do so we need input parameters. So these are called input parameters. Some call them standard notation, lambda. So this is lambda, another Greek letter. It's called the mean arrival rate, sometimes called the offered arrival rate. If it varies, then we have the lambda e, called the mean effective arrival rate. This is the case when customers arrive, find the system busy, and then they leave. So we only focus on those that enter the system, and we call them the effective arrival rate. And this is the mean service rate per server. So if I have 2 servers, each one will be working at rate mu. Okay. And I just want to make sure that the key word here is the word rate. So the mean time between arrivals would be 1 over lambda. Same thing, the mean service time would be 1 over mu. We'll talk about this later. So model notation, since we have so many queuing models to work with, Kendall in 1950s developed this nice notation to distinguish between different queuing models. And basically in the first place he gives a designation for the arrival process. In the second place he gives a designation for service times. Then he gives the number of servers and the system capacity, which means the queue and server, and the population size. So for the arrival process he uses M for exponential or Markovian, D for deterministic, and G for any general distribution, probability distribution. Number of servers can be either 1 or K. K can be 1, 2, 3, 4, etc. The system capacity can be finite, F, or infinite if, as we said, customers never fill the waiting space. And the population size can be infinite or can be finite. In the case of finite, we call it M. Alright, so examples of this, if I have an MD1, there are default values when there is no value restricted. So if I have MD1, that means I have Poisson arrivals, i.e. Markovian or memberless arrivals. I have deterministic service times, and I have single server. MG7 means Poisson arrivals, exponential service times, because they mean the same thing, and 7 servers and infinite waiting space. This means exponential Poisson arrivals, general service time. I only need the mean and the variance of the service time. In this case, I have 7. Oops. Oh, what I did here. So there should be just there's no 7 here, should be just 10 servers. But anyway, in this case will be 7 servers and 10 waiting spaces. And MG7 1050, so that means I have Poisson arrival, general service time, 7 servers, 10 waiting spaces, and 50 customers that can arrive at the system. Okay. So I want to talk about some basic properties. Most of the time, if we collect data, and the input for the system is really customer arrivals and service times. So if we collect data on time between arrivals, or the number of customer arrivals for any unit of time, we'll find that to be a Poisson distribution. So we're going to talk review a little bit the Poisson distribution. So here we assume that customers arrive individually and completely at random. So this is what happens when customers completely arrive at random, don't coordinate with each other like a bank teller. They don't arrive in batches. So we expect in this case that the arrival process is called Poisson. This means the arrival process has stationary independent increment. But the important property is that the number of arrivals during any unit of time is a random variable with a Poisson distribution, which given by this formula, which you have seen before in your probability class. If you don't, so you need to go back and remind yourself of this formula. Where P of x is the probability that x arrivals within the time period. Lambda is the mean number of arrivals per unit time. So it's a rate. It's the mean number of arrivals per unit time is an arrival rate. E is the base of the natural logs, and x is the number of arrivals in that one time period. So this is an example of a Poisson arrival where if lambda equal 1, we have the blue. So these are 3 distributions superimposed on top of each other, and see how larger lambda moves it to the right. The exponential distribution. So here also, if we take service times and do a histogram and graph them, quite often we'll find that to follow this distribution. So we assume service times to be exponential in this case, and if we let t be the service time and assume t have a negative exponential, then it will have the following density function. Ft will be mu e minus mu t. So this is mu, okay, and it would have the following shape. So it follows that the cumulative distribution P of t less or equal to t is 1 minus e minus mu of t. So if I have a t here, that would be the area under the curve up to t. If I want the area above that, it would be just e minus mu t. And the mean of t is 1 over mu. And the variance is 1 over mu square, and the standard deviation, of course, would be the square root of the variance, which would be 1 over mu. So the mean and variance would be the same, and that's the only continuous distribution where the mean and the standard deviation are equal. So I said before that the Poisson and the exponential distribution are similar, So Poisson is discrete, but exponential is continuous. But this is a nice relationship between them. So if the inter-arrival times, if time between arrivals follow an exponential distribution with mean 1 over lambda, means mean time between arrivals is 1 over lambda, then the number of arrivals per unit time will be a Poisson distribution with a mean of lambda, right? Or mean rate of lambda. The other thing is, as you probably know from your probability class, exponential distribution has the memoryless property, which means given that a customer has received this much time, the probability would receive an additional t units of time before leaving is the same as a new customer just starting and leaving after t units of time. So basically, regardless of how much time you have received, if your service time is exponential, the time until you're done is not influenced by how long you've been receiving service. Okay. Talk about general relationships, and this first one is called Little's formula, and it's called L equal lambda W, and we've seen all this notation before. I mean, this is the mean number of customers in the system, this is the arrival rate, and this is the number of how long a customer spends in the system. So if you think of your queue as just a black box where customers arrive, they go in at rate lambda, and then they leave after some time. If you count on average how many in that box, that's going to be the same as the rate at which they arrive and the average time they spend in the system. So here you see a justification for this, but also if you take your system as the queue only, exclude the servers, just the queue, LQ, how many customers in the queue, would be the same as the arrival rate times how long a customer waits in the queue. So Little's formula applies in both cases, whether your system is just a queue or the whole system including service time. So the importance of this is, if I know LQ or L, I can find W or WQ. If I know WQ, I can find LQ. So regardless of what the system is, it's very general. It applies to all queues regardless. So it's a very useful model. There are other relationships. One of those is this. W, the waiting time in the system, is equal the waiting time in the queue plus the service time. Of course, on averages and mean. So the mean waiting time in the system is the mean waiting time in the queue plus the mean service time. From this and Little's formula, we also said the mean number of customers in the system is equal the mean number of customers in the queue plus lambda over mu. And that's true also in general. So which means that if I can find one performance measure, I can find the rest of them from those three relationships. Little's formula, L equal lambda W, or LQ equal lambda WQ, is the same relationship. W equal WQ plus 1 over mu, and L equal LQ plus lambda over mu. So these are very useful general relationships, applies to all queues. So in the next queue, we'll just focus on 5 queuing models and discuss those. Okay, see you in the second video.